Hello friends, welcome back to the chemistry session. We have discussed about the different effects of temperature and other factors on the rate of reaction. In this session I am going to discuss about the effect of catalyst on the rate of reaction. First of all, we must understand what is a catalyst. A catalyst is a substance which can alter the rate of reaction. So catalyst alters rate of reaction. When I say alters, it can be increasing the rate of reaction. It can also be decreasing the rate of reaction. When we add a catalyst and if the reaction rate increases, we call such a catalyst as positive catalyst. And if it decreases the rate of reaction, we call it as a negative catalyst. Now we will see what happens exactly according to the collision theory concept during the reaction when a catalyst is added to it. Let's see that. Now here is a graphical representation of the reaction trend. This we have seen in the beginning of collision theory discussion. You can refer the previous videos to understand these things better. Now I have energy axis along y-axis and reaction coordinates along x-axis. Here A and B are the reactants, C and D are the products. During the reaction, A and B collide with each other and their energy increases to form an unstable higher energy intermediate known as activated complex. That activated complex decomposes into products. This is the theory understanding. Now we will add a catalyst to this. Suppose X is a catalyst added to the reactants. Then what happens? The reaction trend changes. Now it follows a different path. There is a new path being followed. What happens to the energy of activated complex? There will be change in it as we have added a catalyst to this. So there is effectively decrease in the activation energy as well as threshold energy of the reaction. Okay, threshold energy was still here from 0. Now there is a decrease. A little extent of decrease of activation energy and threshold energy has happened due to the addition of a catalyst. So here the important point to be remembered is the catalyst comes out along with the product without any change in its composition or amount of substance. So a substance can be called as a catalyst only when the amount and composition of the catalyst is not altered during the reaction. It only alters the speed of reaction and will not participate or undergo any chemical change during the reaction. So this is the trend of the reaction. There was a path followed by the reactants. Now a new path is being followed. So we say that the old path as path without catalyst. This is path without catalyst. And the new path is the path with catalyst. Yes. So this is the graphical representation of the effect of catalyst on the rate of reaction. Now these two graphs explain the effect of positive and negative catalysts exactly. So I have energy axis along y again and reaction coordinates on x-axis. Same in the other graph, energy versus reaction coordinate. Now in the first graph, if you observe, the blue line represents the normal trend of reaction and the red path represents the effect of positive catalyst. So there is a decrease in the activation energy and threshold energy of the reactant. Whereas in this case, there will be increase in the activation energy as well as threshold energy by the addition of negative catalyst. So what happens when a positive catalyst is added? Rate increases. Rate increases because activation energy decreases. In the second case, negative catalyst causes the decrease of rate of reaction. Rate decreases because of the increase of activation energy. So now we have to give some conclusion about what happens due to the change in temperature and what happens due to the change in catalyst or addition of catalyst for the rate of reaction. Let us conclude that. So, on changing temperature, the rate of reaction is altered. It is directly proportional to rate actually. And that is because on increasing temperature, number of effective collisions increases. And this happens because the kinetic energy of molecules or reactant molecules will increase. When the kinetic energy is more, they collide with greater energy. So it leads to the number of effective collisions. These number of effective collisions increase the rate of reaction. The second is effect of catalyst. Here rate depends upon the catalyst. Positive catalyst I have taken, and it means the positive catalyst decreases the threshold and activation energy. Now the reactant molecules with little lower energy than the required activation energy would also reach the activated complex state and decompose into products. And thereby finally I can conclude that rate is depending on catalyst because catalyst alters number of effective collisions finally. So these are the two conclusions from the collision theory that we can understand. Now based on the concept of effective collision, that is the collision theory proposed by Arrhenius, he could give us a mathematical expression to find the rate of reaction. Here the equation also gives us an idea on what all factors the rate of reaction or effective collisions depend. The effective collisions depend upon different factors. The Arrhenius equation is like this: K is equal to A into e power minus Ea by RT. And here the factor A is called Arrhenius constant. Arrhenius constant A is actually a product of two factors. One is collision frequency and the other is probability factor or orientation factor. Here collision frequency means the number of collisions per unit time. This is number of collisions per second per unit volume. So for a given volume in 1 second, how many effective collisions happen is the factor collision frequency. And the second factor is probability factor or orientation factor. When the collisions of molecules are head to head, the collision will be more effective. If they are at an angle, the effective collision may not happen. So number of effective collisions also is decided with the proper orientation, and these two factors are included in A, which is Arrhenius constant. Now Ea is activation energy, R is universal gas constant, that is 8.314 joule per Kelvin per mole, or R can have different values based on the units used. Then T is temperature. Since I have taken per Kelvin here, I have mentioned it as temperature in Kelvin. So have a look at this equation. We will try to simplify this equation into our calculation purposes. Okay, let's consider this equation. Now I will take natural log on both sides. Yes. So if you take natural log on both sides, there is a factor E, exponential factor here, which will become unity, which is helpful for us for calculation. So it becomes ln k equals ln of A into e power minus Ea by RT. Now simplify the RHS further. This becomes ln A plus ln of e power minus Ea by RT. Okay, once again we can simplify this. Ln A, take this power to the coefficient, which becomes minus Ea by RT. These are the principles of logarithm. As we know, product can be converted into sum here, and power exponentiation can be converted into coefficient or product. So this becomes ln E. This value is equal to 1. So on changing this to log 10, log k to the base 10, even if 10 is not written, it is understood it is base 10, is equal to log of A to the base 10 minus Ea by 2.303 RT. Here there is one small thing I have skipped a step here, and that is when you convert ln into log to the base 10, you have to multiply that with 2.303. So here I'll get 2.303 log k equals 2.303 log a minus EA by RT. But throughout the equation, divide by 2.303 so that they get cancelled here, here, and one more term remains here. So this becomes the simplified form of Arrhenius equation. Now using this equation for the same reaction at different temperatures, we can relate the rate. That we will do now. Have a look at it, please. So let's say K1 and K2 are the rate constants of a reaction at temperatures T1 and T2. Then according to Arrhenius equation, simplified form of Arrhenius equation, we will have log K1 equals log A minus EA by 2.303 RT1. RT1. This is the first expression. Now for K2 with respect to T2, I'll have another equation, that is log K2 equals log A minus EA by 2.303 RT2. So these are the two equations I have obtained from Arrhenius equation. Now let us subtract the second equation from 1. Then the signs change like this. Then what happens? Log A gets cancelled. Then on LHS I will have log of K1 minus log of K2, which is equal to log A has gone minus EA by 2.303 R. If I take this as common factor, I will have 1 by T1 minus 1 by T2. This minus into minus becomes plus. So everything is correct. I can reduce one more step here. Log K1 minus log K2 can be written as log of K1 by K2. Log A minus log B formula, which is equal to minus EA by 2.303 R into, take LCM T1 T2, and here it becomes T2 minus T1. There are different forms of representing this equation. If you play with this plus and minus, you will have these variations. Like if I change this minus to plus, this becomes T1 minus T2. If I retain minus, or if I change this minus, then K2 can be reciprocated. K1, K2 can be reciprocated. In whatever way you want, you can remember the equation. This is very important equation because we are going to solve some numerical problems on this concept. So this is the simplified form of Arrhenius equation. Okay, now let us have some discussion on graphical representations of chemical kinetics chapter. We have already seen the variation of concentration versus time for a general reaction in the beginning. You may refer the first video of chemical kinetics. Later we have also seen some more graphs of collision theory, explanation while explaining effect of temperature and effect of catalyst. We have different graphs. Apart from that, we also have these graphical representations in this unit. So for a zero order reaction, we have derived the integrated rate expression, rate constant expression like this, R0 minus R by T for a zero order reaction. Now I have chosen reactant concentration along y-axis and time along x-axis. And as you can see in the expression, R0 minus R, R0 minus R, which means the value keeps on decreasing as the time progresses, because the concentration of R changes as the time goes. So there will be change or decrease in the concentration with respect to time, and I'll get a equation, a straight line sloping downwards. And now the slope of this will be the negative slope, and that will be the value of K, or let us say K is equal to negative slope. That's all. So this is the representation of a zero order reaction. Now for the first order reaction, the rate constant K gives 2.303 by T log of R naught by R. This integrated rate expression we have derived. There are two ways of representing this. Let me consider the first way, where I'll take this equation in a simplified manner. K is equal to 2.303 by T into log of R naught minus log of R. So I have separated R naught and R now. Then let us transfer this 2.303 to LHS so that constants will be on the same side. So I'll have K by 2.303 giving 1 by T log R naught minus 1 by T log R. Okay. Now once again I'll rearrange these things so that I get log of R on LHS, so that it is 1 by T log R plus K by 2.303 equals 1 by T log of R naught. Okay. The last step, multiply this by T throughout. I'll have log R. Also shift this to RHS, it becomes minus KT by 2.303 plus log of R naught. I hope you can understand this step easily. Now the purpose of writing this equation is because I can compare it with y equals mx plus c, which is equation of straight line. Now I can take log R on y-axis and I can take t, time, on x-axis. Then c, log R naught will be the intercept. Anyway, minus k by 2.303 becomes the slope of this. Yes, let us see the graphical representation. So this is the first way of representing graphically. As I said earlier, I'll take log of R on y-axis, then time along x-axis. Now the line will be in the form of a straight line but with a negative slope. So it starts somewhere here and decreases. So it represents a straight line, and this value, intercept value, will be log of R naught. Okay, C is log of R naught, and slope of this line is equal to minus K by 2.303. Representation of rate constant of first order reaction in this manner helps you in answering some questions in competitive exams. Now we will see the second way of representing the rate constant equation of first order reaction. Directly by relating this expression in this manner, just cross multiply this, you will get KT by 2.303, which is equal to log of R naught by R. Okay. Now I can compare this as y equals, here itself mx plus c. There is nothing, so there is no intercept c. Okay. So compare this. In the graph, I must have log of R naught by R along y-axis, and along x-axis I must have t, that is time. There is no intercept, so the straight line must start from the origin, from here, and it has a positive slope, so I'll have a straight line in the increasing manner like this. Okay, in this case the slope becomes, slope of this is equal to k by 2.303. So it depends on in which way you have chosen the y-axis and x-axis. If it was log of R versus time, we had a straight line inclining downwards. But in this case, there is a straight line inclined upwards and the slope has become positive, k by 2.303. So have a look at this, we will move on. Now finally, zero order and first order rates according to law of mass action. For zero order, we know rate is k into r power 0. Concentration will not alter the rate. So when I take rate versus concentration of reactant, I'll get a straight line parallel to x-axis because there is no change in the rate at all on changing concentration. So the value of this will be k finally. And rate versus concentration for first order reaction will give you a straight line having a slope positive inclined upwards, which is having the slope value k. So this is the representation of first order. Even this difference is important to remember. Anyway, friends, this is the conclusion of our chemical kinetics theory part. In my next video, I am going to solve some numerical problems based on different concepts of this chapter. Keep watching. Thank you for watching this video.